Hello everyone. Today I'm here to talk about blind the kernel, subverting integrity checks via semantic asymmetry. So before I move on to my talk, let me just introduce myself. So my name is Tejaswini and I work as Senior Malware Detection Researcher at Sentinel-1. So I have over 7+ years of experience and my primary focus is on reverse engineering and writing detections on them. So apart from that, I have written various blogs and white papers throughout my career till now. I've also presented at AVA 2021 and I also love to play CTF challenges. I have successfully completed Flare-On 9 and Flare-On 11 challenges, if you know about Flare-On. And so apart from that, I also love traveling and I would also love to explore Prague, and because this is the first time in this city. So yeah, moving on, let me go on to the presentation. So first, before I go in depth into what my presentation is about, let me just give you a small introduction about what a malware is. A malware can be imagined like a chocolate. So you have a chocolate. To eat the chocolate, you have to unwrap it, right? In the same way, a malware is also either packed, obfuscated or encrypted, and then to get the actual content, you have to either unpack it, deobfuscate it and decrypt it. Then after all this unpacking, deobfuscation, decryption, you get the actual payload, and that payload performs process injection. So it's not necessarily that every malware does process injection or process hollowing. It's like a common behavior which is observed in malwares. So you will understand later why am I talking about all this stuff. So moving on to the next slide. So let me discuss about process hollowing, which is a subtype of process injection. So there's a malware process and then there's a target process. Malware process will start the target process in a suspended mode, write down its contents inside it and run from inside the target process. So this is a general overview of process injection or process hollowing. So you can see this here in this animation, how the malware process is actually replacing the target process and running from inside the target process. Now, how is this process hollowing happening, or what APIs it uses? So first, it has to create the target process in a suspended mode. So for that, it uses create process API and creates that particular target process in a suspended mode. Now, what is this target process? It is a legitimate process, like maybe svchost.exe or explorer.exe or any legitimate process of Windows operating system. Now, after creating the process in a suspended mode, it has to now unmap its sections. So the next API called is NT-unmap view of section. So it hollows the process by removing the original executable's memory mapping. Now, it has created the process in a suspended state. It has unmapped the contents of the section. Now it has to allocate some memory space inside that particular target process. So for that, it uses virtual alloc EX. So the next API used is virtual alloc EX, where it allocates some memory space in the target process. Now, it has created the process, unmapped its contents, it has allocated some memory space. Now it has to write the actual payload or the actual chocolate inside that particular target process. And for that, it uses write process memory API. So the next API called is write process memory. Now, after writing the contents into the target process, or after writing the actual payload into the target process, you have to tell the loader from which point or from which step, from which line should I start executing. So for that, set thread context API is used to tell from what is the entry point to the, or set the EIP to the entry point of that particular payload. So for that, set thread context is used. And then the last API called is resume thread. To actually, because we created the process in a suspended state, so you call resume thread to again resume the process. So this is a basic API sequence of a process injection. Again, this is an overview of the APIs used. There may be changes in the APIs. It differs from malware to malware. So now, After knowing about this process injection, I have taken a sample from VirusTotal, and then I started debugging the sample. When I executed the sample in Windows 10, I have seen that it is doing process injection in explorer.exe. Fine. Okay, in Windows 10, that sample is performing process injection in explorer.exe. I was wondering what content it was writing into. So to know what content it is writing into in the explorer.exe, I have set up a breakpoint on write process memory API. So why on write process memory API? Because I know that the parameters of write process memory will give me the memory address and the content being written into the injected process. Fine, I have set the breakpoint on write process memory, and I have seen that execution stopped, the debugging stopped over there, the breakpoint hit there. I've seen the debugger, I've seen the parameters, I've seen the registers. I saw that a PE file, which is a coin miner, is being loaded into explorer.exe. Fine. Now, I have taken the same sample and executed in Windows 11. I have set breakpoints on write process memory over there also, and I found something interesting happening in the debugger. Let me show you the video. I'll just play the video and see. So let me just play the video. Yeah. So you can see that random.exe is executing. It is performing process injection in explorer.exe. It has stopped at write process memory. You can see the parameters that it is doing something in NT-manage hotpatch. And then the third parameter, if I can see, there is some disassembly being written, some assembly code being written into it. And I will disassemble it. You can see that disassembly, something move EAX and some return. So something is being, written into NT-manage hotpatch. Fine. Let me move on. Then there is another trigger at another write process memory. Here I can see a location 10 lakh. Then I can see what content it is being written. So this is the PE file which I was talking about, which is the coin miner, which is being injected into explorer.exe. So you can see that from the process hacker, from the memory section at 10 lakh. So it is private memory, RWX, and then that's the PE file. Now, there is another trigger on write process memory, and that is now on query virtual memory. So, this is interesting. So, let me summarize to you all till now. In Windows 10, write process memory was being hit only once in the debugger, but in Windows 11, write process memory was being called 3 times. Once for the injection, which was happening in Windows 10 also, but there it was being called 2 times to patch 2 functions, which is query virtual memory and NT-manage hotpatch. So moving on to the next slide, here we come to the core of our topic, twin patch evasion. So why it is patching these functions, what are these functions, and how the patching is done. So let me move on and explain to you each and everything. So, what is query virtual memory? Query virtual memory is an API which gives you information of a specific memory page of a particular process. So, what information do you get? It is state, type, and protection of a particular memory page. So, you can see its parameters here. The first is the process handle. That means for which process you require the information. And then the address or the memory address of that particular process, for which address you're querying the information. And the third important thing, memory information class, which is what type of information you want. So let me explain you via this snippet. So this is the memory map of explorer.exe. You can see all the DLLs loaded here, the memory addresses, and then this is the type. Type means if it is mem image or mem private, the state if it is committed, reserved or free, and then the protection if it is read, write, executable. So you get all this kind of information. So if I want for the first memory address, then you can ask for state, type, protection. So this is an overview of query virtual memory. Now, we come to the next question. What is the need for malware authors to patch this query virtual memory, and that too only in Windows 11 and not in Windows 10? So, you can understand that there is something new in Windows 11 that malware authors are forced to make these changes. So what are those changes? That is what we are going to talk about. So Windows 11 24H2 has introduced support for native hot patching. So before I talk about hot patching, what is a patch? A patch means change or code in some function. Right. So patching means you're changing some code in some particular function. So for doing patching, you're actually doing it on some core system file. And that core system file might be in use, and you have to restart your machine to replace the old file with the new one so that the Windows machine will again start working properly. Right. But for patching, all this is needed. And one more thing, why Windows does these patches? Maybe to fix some security vulnerabilities, or to fix some bugs, or for some performance or usability upgradation. Right. So when you're doing these patches, and between the applying of a patch and between the restart, so there might be a time gap in which there might be attacks which might happen. So Windows 11 has come up with the support of hot patching. Hot patching means you're actually updating the code or the memory on the fly, and there is no need for you to restart the machine. Now, how is Windows able to do this? And how the latest versions of Windows are able to do this? So first, it has introduced few new things. The first is new SCP CFG system introduced along with hot patching. Then there are 4 new sections in NTDLL, self-contained CFG functions, and then the 4th one, extra 4 KB space reserved at the end of each DLL. So let me talk about and go through about each of them in the coming slides. So you can see this snippet of Windows 11 NTDLL, which is having extra 4 sections. So this sections are named like SCP CFG and stuff like that. Now, this is a snippet in Windows 10 NTDLL, and you can see clearly that these sections are absent. Moving forward, I was talking about SCP, CFG and all right now, before the slides. So what is CFG? CFG, I guess most of you all might be knowing, it means control flow guard. That means it will validate the indirect call if it is going to the legitimate target address or not. So this is the basic definition of CFG. For how does it validate? It actually creates a bitmap of all the target addresses, and then it will match if that indirect call is actually matching perfectly with the target address or not. Fine. So in CFG, you can imagine like a guardrail, like if the call is going perfectly or not. Now, hot patching also means you're making some changes to the code. That means you are actually injecting something, right? Kind of process injection only, right? You're injecting something. So how will Windows or the OS understand that this is hot patching and it is not any malware performing the process injection? Right. So because of the CFG checks, because of the strict CFG checks, this hot patching might fail. That is the reason why, to allow hot patching to work properly in the latest Windows versions, there is a support for SCP CFG. SCP CFG means that it is a position independent functions, self-contained, they are present. So where are they present? How is hot patching going to work along with this? I will discuss with you in the coming slide. So I have talked about extra 4 KB space. So in this image, you can see clearly that I have actually taken explorer.exe's memory map. So you can see clearly that in Windows 11, for every hot patchable DLL, there is an extra space reserved. That is image reserved. So there's an extra space reserved for every hot patchable DLL, and this is the house of SCP. So whenever there is hot patching, it will directly go into this space and utilize this space, and this space has all the pre-compiled localized CFG versions inside that particular place. So this is the biggest change in Windows 11, that introducing the extra space reserved for the SCP. So with this, you will not touch the original unmodified memory, and hot patching can take place properly. So this is fine. These are all the new changes in Windows 11. Now, Why are malware authors patching query virtual memory? How are these changes in Windows 11 linked to the patching of query virtual memory and patching of NTDLL managed hotpatch? So, I've talked about process injection earlier. So in process injection, the last step is resume thread. So after resume thread, it will go to the entry point of the payload and execute from there. So between the resume thread and going to the entry point of the payload, there are few loader calls which happen. So first is LDRP initialize process, which initializes the process, and second is LDRP process mapped module. So when you create a process in a suspended state, only NTDLL is loaded. So to load the other DLLs, when you are actually resuming the thread, this API is called. Then there is another call which is RTLP insert or remove SCP CFG function table. So this is a new API which is being called only in the Windows 11 latest versions. So this actually talks about SCP CFG function table, which should be added or not, and this table can only be added in a hot patchable DLL or an executable, right? So that hot patchable DLL or executable should be actually physically present on the disk, right? So that means the memory type should be mem image, but in our payload or whatever our payload we are injecting, because we are virtually allocating that memory and then injecting the payload, that memory type would be mem private. Because of the conflict of mem image and mem private, this RTL insert or remove SCP CFG function table will fail. How is this API being failed and giving errors? Because this API internally calls query virtual memory with E. That means memory image extension information class. So it is querying information E, and if it is querying the memory address where our payload is actually loaded, then this will give you an error because you cannot make a SCP CFG function table for a mem private that doesn't physically exist. So because of the mem image and mem private conflict, this actually throws an error and you will get var fault and your payload will not execute in Windows 11. So any process that actually performs process injection or process hollowing will not execute in Windows 11 if these two functions are not patched. Now, moving on. How patching is done, how this patching has been implemented in the malwares which I was showing you. So first, I have given a basic overview of how the patching is implemented. First, when the query virtual memory is called, is the query type memory image extension information? That means is that class being asked is equal to E? And if the query type's address is matching our payload, if these two matches, then please return status not supported. That means you're telling that this function is not present. You're actually blinding that this function is not present and just return status not supported. If the query is not related to our payload, and if it is related to our payload and it is not matching to E, then please proceed to the and execute the function query virtual memory directly. So now I will show in the next slides how this has been implemented in the malware. So first, to go to that particular address, you have to use the get module handle, get the handle of NTDLL, and then you use query virtual memories and use the API get proc address. With the parameter query virtual memory, you get the address of that particular API. Now, after that, the malware actually allocates a space, a 4 KB space, to the trampoline code. So let me explain you what this trampoline code is. So, whenever an API which is there, like you can see the API, there's query virtual memory, then there is a syscall. Now, the first line is actually a NOP pattern. So that NOP pattern is present between the APIs, that's common. So this malware is targeting that NOP pattern and replacing the first line with jump to patch space. So the first line will get executed before actually going to the actual call of query virtual memory. So it will jump to patch space, see what is present in the patch space and then come back to this. So let me show you what exactly is in the patch space. Now, patch code in the patch space, this is the actual hook logic. So I've told you in the flowchart already, if the parameter is E, and if it is querying our memory address or the malware's payload, if the memory address is equal to the payload, then please say that this API is not present. Return status not supported. So that move EAX and that code which you can see there, right? That is the status code for status not supported. Otherwise, please proceed and execute query virtual memory normally. Now, moving forward, I've talked about another evasion, another patching, that is patching on NT-managed hotpatch. So NT-managed hotpatch is a system call that implements Windows hotpatching functionality that needs the ability to run the code without restarting. So you can see the parameters here. So why are malware authors actually patching this particular function also? So here, in this particular function, I've talked about resume thread and going back to the entry point. Their loader also calls LDRP query current patch, where the Windows keeps checking like if there is any hot patches to be applied or not. So again, here also it fails because of the conflict of mem image versus mem private, and then your execution will stop. So that's the reason why malware authors are patching NT-managed hot patch. So here you can see the write process memory call and the parameter NT-managed hot patch and what actually it is writing into that call. So it is writing this particular assembly. So if you disassemble it, you can see that it is writing move EAX, a status code that is again status not supported, and return. So let me summarize what I've told till now, before and after patching of ZW query virtual memory. So first snippet which you can see is of NTDLL, which was normally present like in the machine. You can see that that particular file offset has the proper function for query virtual memory. This second snippet which you can see, I have taken dump of NTDLL of explorer.exe. So that's a memory dump of explorer.exe's NTDLL, and you can see how that first line is patched there. So the same way for before and after patching of NT-managed hot patch, you can see the actual original function in the first snippet, and in the second snippet you can see how the status not supported assembly code has been put there. So this is about the twin patch evasion. So I have written a small rule, a hunting rule basically on virus total, and related to how it is patching, like what all, based on the assembly codes I have written a rule, and I can see that 6,300 similar malwares are found on VT, on virus total, and there are various families found like Agent Tesla, Remcos, Snake Keylogger, Asyncrat. So there were many compilers also like .NET, C, VB. So many different compilers, many different families have adopted this patching already. So coming to the summary, evasion is rapid. So whenever Windows makes any changes, malware authors are also updating themselves. Like already PureCryptor and GhostScript have already implemented this bypass, like just after the few weeks of 24H2 release. Then the detection focus. Detection should not rely completely on the OS level mitigation. So you should even monitor on important calls like write process memory if they are targeting system DLLs such as NTDLL, and that too on a newly created suspended process. So that's all about the summary. So you can see the references here and the few hashes. So first hash is about the malware I executed. So you can execute the sample, check in Windows 10 and Windows 11. I have provided the samples. And the second is a Hazer Shades blog. So it has a complete POC related to similar stuff. So yeah, thank you. Thank you all.